Hi everyone, my name is Brant Robertson. I'm a professor of astronomy and astrophysics here at the University of California, Santa Cruz, and I'm here to tell you about the amazing James Webb Space Telescope that NASA will launch into space in just a couple of days. James Webb Space Telescope is one of the most amazing scientific facilities ever created. You may be quite curious about the properties of the telescope, where the telescope will orbit. Does the telescope have a hot and a cold side? Why is it an ambitious piece of engineering? Well, today we're going to explore these questions and more, including what we'll learn from Webb's images and data. Here you see a beautiful computer rendering of how James Webb Space Telescope might appear in orbit. You can see the large primary mirror constructed from gold-plated hexagonal segments. In front of the primary mirror, you can see the secondary mirror support structure that guides the light reflected from the primary mirror to the instruments mounted behind. You can also see the large heat shield that keeps the telescope cool. Webb has a 6.6 meter, 21.7 foot diameter primary mirror. It's quite large, and that's for several reasons. For context, Hubble's mirror is much smaller at 2.4 meters, about 7.8 feet in diameter. Webb has to have a bigger mirror to capture high-resolution, Hubble-like details in infrared light. Its mirror also needs to be stable at very cold temperatures, 40 degrees Kelvin, which is roughly minus 390 degrees Fahrenheit, which is why it's made of beryllium, a material that is 6 times stronger than steel and 2/3 the density of aluminum. There are 18 hexagonal segments. They are hexagons, so the mirrors can be adjusted to align without gaps and to form a circular shape. Each segment is coated in a very thin layer of gold, about 1,000 atoms thick. Gold was selected because it is the best reflector of infrared light. Webb orbits the Sun near the second Sun-Earth Lagrange point, often referred to as L2, a point where the gravity from the Sun and the Earth balance. This point is approximately 1.5 million kilometers, that's about 930,000 miles, from Earth on the far side of Earth from the Sun. Webb can't orbit the Earth like Hubble because the visible and infrared light from the Sun, Earth, and Moon would heat up the telescope's mirror and scientific instruments, causing the telescope itself to glow in infrared light that would outshine the faint objects in space. Webb will not be located precisely to L2, but will move in a halo orbit around L2 as it orbits the Sun. At L2, Webb can maintain a safe distance from the bright light of the Sun, Earth, and Moon, while also maintaining its position relative to Earth. The lower part of Webb, where its 5-layered sun shield is, faces the Sun. This is where its equipment that does not need to be cooled, like its solar panel, antennae, computer, gyroscopes, and navigational jets, are located. Its tennis court-sized sun shield protects Webb from external sources of light and heat, which ensures that it can detect faint heat signals from very distant objects. It's very important for its observing side to be very, very cold. Webb science instruments are housed behind the mirror, separated from the warm communications and control technology by the sun shield. Webb needs both passive and active cooling. Its 5-layered sun shield provides passive cooling. The first layer of the sun shield is 2/1000ths of an inch thick, while the other 4 layers are only 1/1000th of an inch thick. In 2021, Webb was carefully folded up and loaded onto a ship, which passed through the Panama Canal on its way to French Guiana in South America, where it reached its launch site at the European spaceport located near Kourou. It is beneficial for launch sites to be located near the equator, since the spin of the Earth can help give an additional push to the rocket. After launch and during the first month in space, On its way to the second Lagrange point, Webb will undergo a complex unfolding sequence. First, deploying, tensioning, and separating Webb's sun shield will occur. This is the 5-layered diamond-shaped structure you saw in the previous graphs. Then it will extend its secondary mirror support structure and unfold its primary mirror, the one with the honeycomb-like pattern seen in previous slides. Deployment and commissioning will take time, at least 6 months. Engineers and scientists will carefully activate and confirm each and every instrument is working properly before the first, but still unfocused image of a star field is delivered about 2 months after it launches. In the 4th month after launch, Webb will complete its first orbit around L2 and take the first focused image. This will show that the mirrors are aligned. After the 6 months mark, Webb will begin its science mission and start to conduct routine science operations. The Space Telescope Science Institute in Baltimore, Maryland, plays a key role in communicating with Webb. It hosts Webb's Mission Operations Center, where engineers and scientists command and control the telescope. Commands from Space Telescope travel to the Deep Space Network, or DSN, which transmits them to Webb. Webb's data then return through the Deep Space Network to Space Telescope, where the data Webb took are then processed, distributed to the scientific community, and archived. Now we're going to talk about some of Webb's capabilities and some of the science that James Webb Space Telescope will do. Let's start with infrared light. What is infrared light? Well, the rainbow of light that the human eye can see is a very small portion of the total range of light, known in science as the electromagnetic spectrum. Telescopes can be engineered to detect light outside the visible range to show us otherwise hidden regions of space. Webb detects near-infrared and mid-infrared wavelengths, the light beyond the red end of the visible spectrum. Let's look at this concept with more familiar objects. Visible light provides us with detailed information about our environment, including colors and textures, as seen with these meerkats and freshwater crocodile. In infrared light, we see different details. The meerkats glow dramatically. Their high metabolisms cause them to glow brightly in the infrared through insulating layers of fur. The freshwater crocodile, on the other hand, is faintly brighter than the cool ground, which tells us it had recently been lounging in the pool of warm water in the lower left. It's been out of the water long enough to start to cool down. Infrared is a type of light our eyes cannot see. It's redder than red light. Everything is glowing, even if we can't see it with our eyes. Many things like computers and humans and animals glow in infrared light. As the most ambitious and complex astronomical space observatory ever, NASA's James Webb Space Telescope will deliver amazing science, complementing the spectacular scientific discoveries made by other space science missions. Webb will match the incredible image quality offered by Hubble, but with infrared light instead of visible light. Webb, Hubble, and many other observatories will work together. They will target some of the same regions of the sky to provide simultaneous or follow-up observations in infrared light. Using infrared imaging at unparalleled sensitivity and resolution to detect the faint infrared light, Webb's discoveries will revolutionize and enrich our understanding of the universe. By specializing in infrared light, Webb will be able to see what's behind the dust we see everywhere in the universe. The Eagles Nebula's pillars of creation were captured by Hubble Space Telescope in visible light on the left, and near-infrared light middle, and the Spitzer Space Telescope in the mid-infrared light on the right. Like Spitzer, Webb will be able to see through the dust in regions like this, but at high resolution like Hubble. What does each type of light show? Well, in the visible light, forming stars are inside dense cocoons of gas and dust, which block their visible light from reaching the telescope. Near-infrared light shines through all but the most densest dust, revealing many of the stars inside and around the pillars. Mid-infrared light shows the eroded pillars of gas and dust glowing with heat from bright young stars. Webb's images help us see past dust clouds and figure out what's going on in these dense regions in great detail for the first time. One of the amazing capabilities of James Webb Space Telescope is to stare deep into space. On the screen, we have here the Hubble Ultra Deep Field. I was a part of the team that took the infrared part of the Hubble Ultra Deep Field in 2012. The Hubble Ultra Deep Field contains approximately 10,000 galaxies that extend back in time to within a few 100 million years of the Big Bang. The image on the screen actually combines data from many observatories looking at that same patch of the sky. When we look out at space, we are looking back in time. The light arriving at Earth from the faintest objects in the universe is light that left those objects billions of years ago. When we see those objects, we see them not as they are today, but as they appeared long ago. We want to see even more of that light, to see the first galaxies, but that requires we switch back to gathering infrared light in a great new observatory, James Webb Space Telescope. As light travels through the expanding universe, light is stretched into longer wavelengths, which is called cosmological redshift. Light from stars that is emitted as ultraviolet light and visible light is stretched to the longer wavelengths of infrared light. This is the light that Webb will capture, and how it can observe extremely distant galaxies. James Webb Space Telescope will help us find extremely distant galaxies. The galaxy that you see in the inset on the right is named GNZ11, and it's the most distant galaxy that we currently know about. GNZ11 was observed as it was 13.4 billion years in the past. That's only about 400 million years after the Big Bang. Webb will show us even more galaxies that existed in the early universe, and hopefully galaxies even further away than GNZ11. Researchers will examine individual galaxies in Webb's images and data. They will pinpoint how old each one is, leading to Webb's next science capability, studying galaxies over time. By viewing the universe at different distances and eras, we have evidence that galaxies change over time. They grow, they collide, they merge with each other. The most distant and earliest galaxies we have seen tend to be smaller and less structured than those in the nearby universe. However, the earliest galaxies in the universe are still undetected. This is because the universe is expanding, and as space itself stretches, so does the wavelength of the light from the first galaxies into the infrared light. Webb will examine these early galaxies and eras that followed in new detail, providing essential insight and helping us learn more about how galaxies evolve. What's great about this is that Webb's observations will be added to Hubble's, so we'll learn even more about dust, stars, and galaxies over cosmic time. Webb will also help us learn more about the history of the mergers and growth of galaxies, black holes, and the history of star formation. Webb will study black holes both near and far. In our own Milky Way, Webb will peer through obscuring dust to study the center of the galaxy, specifically at our resident supermassive black hole Sagittarius A star and the stars that orbit it. In nearby galaxies, Webb will take high-resolution spectra or data to learn about the temperatures, speeds, and compositions of the material at their centers. Researchers will use this data to measure the mass of the black holes at the centers of galaxies by mapping speeds of the central gas and stars. Webb will also study the feedback loop between central black holes, their powerful jets, and the formation of new stars in those galaxies. Quasars are another type of very distant but very bright active supermassive black hole. They are among the brightest objects in the distant universe. These supermassive black holes, typically located at the centers of galaxies, are millions to billions of times the mass of the Sun. They feed on infalling matter and unleash fantastic torrents of radiation, outshining all of the stars in their host galaxy combined. Webb will study the properties of quasars and their galaxies, and how their black holes influence the first stages of galaxy development in the very early universe. Webb could also help address broader questions of how galaxies form, including the long-standing problem of which came first, the galaxy or the black hole. Thank you so much for listening today and learning about James Webb Space Telescope, NASA's next great scientific observatory. If you're interested in learning more about James Webb Space Telescope, please visit us online at jwst.nasa.gov.